All right, let's take a look at these. Remember, on significant figures, we're looking at how accurately do we know a number. I showed you how we had that slide where we're measuring the same thing with two different rulers. One ruler was able to get it more accurately, so we could have more significant figures. I think it was 5.4 on the one ruler, 5.36 on the other ruler. Well, when we add numbers together, we're asking a very similar question. So let's look at number A right here. And let's line this up. We've got 9.74 plus 8.532. We're adding these up, and what we want to ask ourselves the question right now, when I add them up, what is the appropriate level of accuracy to report the answer? Well, notice that the 9.74, we know the 9, so we know the ones place. We know the 7, we know the tenths place. We know the 4, that's the hundredths place. We don't know this. That digit is uncertain. 9.74 what? We don't know. We've got to shrug our shoulders, right? So 2 plus a shrug your shoulders is a shrug your shoulders. I'm going to say 2 plus that is 2, but just keep in mind that's got a question mark around it. Is that 3? Is it 4? Is it 5? Is it 7? We don't know what the question mark is. The question mark can be anything from 0 to 9. Okay? So we only know this number to the level of accuracy of the least accurate number. 9.74 is the least accurate number. So we cannot report an answer any more accurately than that. So I will add this up. 12, 17, 18.272, and I'm going to round it off to 2 decimal places because my numbers, both of my numbers, have 2 decimal places, but not 3. So I look at that 2. The 2 is less than 5, so the real answer here is 8 point, what happened? 18. I know what I'm doing. I'm right there. Okay, let's do that. So the real answer here is 18.27. You follow that? Kind of get that? Yes?
So are we doing decimal points or significant figures? Because the number with the least amount has only 3 significant figures.
We're doing decimal places in this case. We know without any uncertainty the hundredths place for every number. So we can go there. And we do know that 9 plus 8 is, 9 and 8 is 17 plus 1 is 18. We know that. Okay? So we're not doing significant figures. We're going to do that on multiplication and division, but not in addition and subtraction. Addition and subtraction, we go out to the accuracy of the least accurate number. 9.74 has 2 decimal places. So we're going to report an answer with 2 decimal places. Let's just do one more here. 9.673. Same thing with subtraction. And this is the best way to do addition and subtraction. Not the way I'm giving it to you here. Line it up. Line it up. And you can go ahead and do that. We don't know this, but let's say it's 0. So that's 3, 7. 0 from 6 is 6. 8 from 9 is 1. But we only know this right to there. So what do we do with the 7? Well, we know that that's at least a 7, so 7 is greater than 5, so we will round this off to 1.7, to 2 decimal places. Addition and subtraction are the trickiest ones, and I'm not going to even worry about C. C, just do it in 2 steps. Do the 10.848 plus 1.17, get your answer, then subtract your 0.91. But you do have you have 2 decimal places in that number, you have 2 decimal places in that number, you have 2 decimal places in that number. So you can go ahead and do the math, the addition and subtraction, report your answer to 2 decimal places. Yeah, we're not going by significant figures, we're going by decimal places. This is for addition and subtraction. Okay, do 32A. So what is the final answer you should report? 5.65. That's 5, so we're going to round the 4 up to 5. And we're going to keep the 2 decimal places for each number. Each number has 2 decimal places, so we're going to keep 2 decimal places in our answer. All right. Okay, now, that's the hard one. We've just done the hard lifting right there, addition and subtraction. Multiplication and division, take out your calculators. Multiplication and division is a little simpler. You do go by significant figures. The number that has the least number of significant figures dictates then the number of significant figures in the answer. So this is for addition and subtraction, or even if you are doing, multiplication. This is for multiplication and division, and even if you are doing multiplication and division in the same problem, all you need to do is look for the number with the least number of significant figures. So our rules for determining significant figures is very important in figuring out what to do with the multiplication. So here we got 52 times 643. How many significant figures does 52 have? 2 significant figures. And 643. How many? 3. So how many significant figures are going to be in the answer? 2. So take your calculator and multiply 52 times 643. And notice that's not right. 3 is this what you get? 33436? All right? Notice that your calculator doesn't know how many significant figures to give you. It's how many significant figures are in that number? 5. So we need 3 significant figures, 2. This is our least accurate number. 2 significant figures. So what are we going to report as an answer? 33,000. The 4 is less than 5, so we're going to leave the 3 unchanged. And 33,000 has two significant figures, right? Two significant figures. Okay, let's do C. C is a little bit more complicated. We're going to multiply and divide. So how many significant figures in 2.317? 283. 0.0821. 3. All right, those are leading zeros. Those are leading zeros, and they're not significant. The 821. Trailing zeros are significant. If there was zeros after the 1, they'd be significant. But there aren't zeros after the 1, so just 821, so we got 3. So the answer should have how many significant figures? 3. Okay, now go ahead and do the math. You can do all the math. 2.317 times 283 divided by 0.0821, and then round that off to 3 significant figures. Okay, now these are cases where you are smarter than your calculator. And you need to be smarter than your calculator. All right? Your calculator is a tool. There's a human being holding that tool that has a brain. I mean, we get so enamored with our electronics today that we think somehow, that they're better than humans. They're not. Human beings far exceed any electronic device you hold in your hand. But they were made by human beings, all right? So the internet now has got this big kind of debate going on about artificial intelligence and whether that's going to exceed humans and it's kind of wild. They're starting to say artificial intelligence is almost getting right up there with human intelligence. But artificial intelligence is working off of algorithms and assumptions and everything that human beings have put into the artificial intelligence. All right? So we've got to stay ahead of our phones, all right? And our calculators. Here's a case where you are smarter than your calculator. All right, now round this off to 3 significant digits. You see all those numbers there. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 significant digits. Now, if you report that answer, what you are starting to do right now is say that my answer is actually more accurate than my data. The accuracy of the number you're reporting is exceeding the accuracy of the data you collected. You see what's happening there? We don't know this that accurately because we only know this to 3 significant figures. We don't know it to, what did I say, 4, 8, 10 significant figures. That's an extremely accurate number. But the numbers that went into the calculation aren't that accurate. So this is greater than 5. So that's going to jump that 8 up to a what? A 9. So the answer is going to be 7990. No decimal place after it. If you put a decimal place after it, you've just said it's 4 significant figures. So we round it off to 7990. I don't know, maybe you can appreciate this in terms of presidential elections. I don't know, but let's just look at a case. Here's candidate A. Here's candidate B. The polls, we're 2 weeks out from the presidential election. And what do we find in the polls? That candidate A has 51% of the vote, and candidate B has 49% of the vote. Who's going to win? Depends. Depends on what? How accurately do we know these numbers? And so the newscast says candidate A is, the polls have candidate A at 51, candidate B at 49, with a plus or minus 3% accuracy in the data. So what is candidate A? Well, candidate A has anywhere from 48 to 54% of the vote. Candidate B has anywhere from 46 to 52% of the vote. How do we know who's going to win? We don't. And usually after a broadcast like that, they will say candidate A is at 51, candidate B is at 49, but it's too close to call. Too close to call. What are they saying? Our data has such a level of variation in it, uncertainty. It has such a level of uncertainty in it that we cannot say that 51 is greater than that 49. Is 51 greater than 49? Yes, but the accuracy of these two numbers do not support this number being categorically, you can't put your money on this candidate and say that he or she is going to win the election. We don't know. The uncertainty around the data is there's a level of uncertainty such that it's too close to call. All right? You can't go to bed and say, oh, my candidate's won. You got to wait until the results come in because we don't know. They called 1,000 people, and they should have called 100,000 people. If they called 100,000 people, they might say that our accuracy is 0.5, plus or minus 0.5. And now you'd say, I think candidate A is going to win. You follow me? This is what level of accuracy of data has to do with what is appropriate to report. It'd be very inappropriate to say that he's got 51.7% of the vote. The accuracy is in this, the level of variation is in this digit right here. So to even report a 0.7 is meaningless because of the level of accuracy. Now, if that was a level of accuracy, then you would start reporting it like this. Okay. Scientific notation. See that? That doesn't even right. It's pretty good. Just a little trick. All right, right here. Let's look at scientific notation. I have some slides. Yeah, we might as well look at the slides and then come back to this. I have to scroll up and down through here because I attached this little exercise sheet. All right, let's look at scientific notation. We're going to deal with some very big and very small numbers. We're going to represent them in powers of 10. 4,300 is the same as 4.3 times 1,000, which is the same. 10 to the third is 1,000. 10 to the third is 10 times 10 times 10. 10 cubed is 10 times 10 times 10, or 1,000. So when I just want to point out and make the point right here that when we represent a number in scientific notation, we haven't changed its value at all. It is the same number. 4,300 is equal to 4.3 times 10 to the third power. And we have 3 zeros. 1,000 has 3 zeros. We're moving this decimal point over 1, 2, 3 places. And that's where we get that. To get it back to its original form, we have to multiply it by 10 3 times. So when we move the decimal place to the left, for each place we move it to the left, we add another exponent to 10. So if we had 57,000, now there's no decimal point there, but the decimal point is here. It's assumed there. So we're going to move it 1, 2, 3, 4 places. And so we put 10 to the fourth power. 10 to the fourth power. To convert a number greater than 1 to scientific notation, the original decimal point is moved x places to the left, and the resulting number is multiplied by 10 to the x. So 53 million becomes 5.3 times 10 to the 7th. And we are always moving it. We're doing it so that we have a number that's between 1 and 10. In other words, you say, well, what about if I moved it right there? Then it'd be 53 times 10 to the 6th. That's also equal to 53 times 10 to the 6th power. We've only moved it 1, 2, 3, 4, 5, 6. But that's not the way I want to see you report or convert it to scientific notation. Always move it over to where you have one digit and then the decimal place. So you got a number between 1 and 10. In other words, move it as far over. Don't move it over to here. Move it right there. You got a number between 1 and 10. 5.3 is between 1 and 10. So we get 5.3 times 10 to the 7th. And then if the number is less than 1, like this, we're going to move the decimal place to the right to make a number that's between 1 and 10. So to do that, we got to go 1, 2 places over. But now the exponent is going to be negative. Well, let's just do an easy one here. If I got 0.1, that's equal to 1.0 times 10 to the minus 1. We've just moved it over one place. That's the same as taking 1 and dividing it by 10. We're dividing. We're not going to be multiplying. 10 to the negative 1 is 1 over 10. So we're going to be dividing it by 10, and that gets us back to our original number. So for every place you move it to the right, you have to put a negative exponent of that number of places. So 0.00, this one here, 0.000430, we're making a number between 1 and 10. 1, 2, 3, 4. So we get 10 to the minus fourth, 4.30. Now we're going to keep that 0 because that's a significant 0 right there. All right, that is a significant digit. It's a trailing 0, so keep it. All right? Okay, let's keep that in mind. And let's go to this worksheet and do problems 22 through 30. And while you're doing that, I will take attendance. Okay, let's just get a couple of these. Number 22 is what? 1.216 times 10 to the second. Okay, now in these cases, don't kind of put together scientific notation and rounding. Just don't round the number off. As many as significant figures that are in the number originally, try to keep them in the scientific notation number. So the 23. 1.234 times 10 to the third. All right, these numbers here are not significant. We're going to be moving the decimal point over. All right, someone else here, number 24.
1.86 times 10 to the fifth.
All right. All right, number 25, someone else.
1.25
Times 10 to the minus what? 3. Okay. All right, number 26, someone else.
2.6507
Okay. 2.6507, okay. We're going to drop those 2 zeros. And how many places did we move it? 6 places. All right. Okay, Blessing, let's let someone else do this next one.
6.02 times 10 to the 10th power.
10th?
Yes.
All right. Number 28, I'll do that 2.4393. We're going to keep all those numbers. But we have moved it now 1, 2, 3 places. All right. 4.56 times 10 to the what? And 7.9 times 10 to the 7th. Okay, and none of those are, there's no decimal point there, so none of those zeros are significant. Yeah, and just to maybe just point out one other value of scientific notation. One value is like, well, you can see it on particularly can see it on number 27. That's a big number to write. 602, and then we're writing about 8 zeros after it. We don't have to write all that. It's a shorthand way of writing a big number. We're going to be seeing a number like this. .02 times 10 to the 23rd in chapter 4. We're going to get to the mole, and that is a mole. And you don't want to write 602 and then 21 zeros after it. Uses a lot of paper, uses a lot of ink. It takes a lot of time. There's a nice way of doing it. But another value of scientific notation is, let's say that we knew that San Antonio had 1,300,000 people in it. And you look at that and you say, boy, there's 5 zeros after. There's no decimal point. But let's say we know for sure there's 1 million. We know there's for sure 300,000. There isn't any 10,000. There isn't any of this. And we don't know this. So we got 5 zeros, and 2 of them are significant zeros, and 3 of them are not significant zeros. We can't put a decimal point at the end of it. It makes it look like they're all significant. But what we could do is we could report this number like this, as the population. If we did a census, you did a census and you actually had the data, and you said, yeah, there's 1,300,000 people here, and then some hundreds. We don't know whether it's 400 or 700 or 756. We just don't know these last 3 digits. But we do know all of that. You can actually show that now. That has 4 significant figures. This number here has only 2 significant figures. So when you have accuracy that goes beyond what you can actually just write out as a full number, you could represent it in scientific notation and preserve the accuracy of the number. So just keep that in mind. On the math quiz, I had this problem. I think I had that problem. So it solved that. And you know, when you get into scientific notation, you might have problems like this. You know, and you go, well, what do I do with this? Well, if you have the same number with different exponents, either multiplying or dividing, if you're dividing, you can move this up in here and it's like, and change the sign. Dividing by 10 squared is the same as multiplying by 10 to the minus 2. And then you add the exponents. So you got 10, 4 plus a minus 2 goes to 10 squared, or 100. So get familiar with just kind of how do you handle exponents. So this number here could reduce down to this, and it's times 10 to the 23rd times 10 to the minus 10, or times 10 to the 13th power. So it's going to be 6.02 divided by 1.73 times 10 to the 13th. This is how I'm handling those exponents right there. Okay, now to say a little bit more about dimensional analysis, let me give you this problem. Calculate the number of seconds in a week. All right? Calculate, take out your calculator, little piece of paper. Calculate the number of seconds in a week. Here's a word problem. more than that. Now don't worry about the number. Get a number and write down a number. But what I want to really focus on right now is the method, the process by which we solve a problem like this. I'm starting with a problem that is fairly straightforward. Most of you have a number? Yes? Okay. All right. Now, if you got the right number, you worked with some conversion factors. And let me just list them. 1 week equals what? How many days? 7 days. 1 day equals 24 hours. 1 hour equals 60 minutes. And 1 minute equals 60 seconds. Okay, if we've done nothing yet, we have at least shown that you know a lot of conversion factors. These are conversion factors. These are equivalents. A week is equal to 7 days. Now, this is what's given in this problem. What I've given you is a week. And I'm asking you to calculate the unknown or desired. This problem, the desired result here is seconds. I'm going to convert a week into seconds. So I'm going to start right here with 1 week. And I'm going to convert my week into days. By multiplying by 7 days per week. That's true, right? Now, dimensional analysis says a week in the numerator and a week in the denominator will cancel one another out, become the number 1. So I'm now converting my week into days. And then I can put 24 hours per day. Days cross out. I've just converted my days into hours. And then I can put here 60. Now notice what I'm doing here. How do I know where to put? I want to convert my hours into minutes. Now, where do I put my minutes? Well, I'm going to put my hour down here. Why? Because I want it to cancel out with hours. So I put 1 hour here, and it's 60 minutes. So my hour crosses out, and now I have minutes. My conversion factor can be used any way I want to use it. I can put minutes in the numerator or minutes in the denominator. It's the problem that tells me where to put it. I want hours to be converted into minutes, so I need to put hours down in the denominator so it will cross out here. Do you follow me? I'm walking my way over to my desired unit, which is seconds. I'm walking my way over there. So finally, I got 1 minute down here. That's going to cross out my minutes. There are 60 seconds in 1 minute. And now I've got this equivalence here. I got this equal sign. And notice that the only unit on the left is seconds. Therefore, that is going to be the unit in the answer. When you put an equal sign, you are saying that everything over here is equivalent to what is over here, numerically and unit-wise. They're equivalent, okay? And dimensional analysis is showing me how to get from here to there. Now you may think, man, I got there a whole lot faster just by just kind of gut feeling about this whole thing. But you're going to be hit with a whole lot of problems because you're not going to have any gut feeling about it. You're going to say, my gut hurts. I don't like this. I don't know where to go. This is going to be your scout. This is going to lead you to the right answer. If you will follow the units. Follow the units. All right? So now, the other thing I want to break you the habit of. Don't be rushing to get a number. Okay? I don't even pick my calculator up until I have laid the problem out properly. Am I going to multiply and divide meaningless numbers together? I don't even know if I'm doing them right. So why should I even pick up my calculator? I don't pick up my calculator until I get to this point. I've got seconds on the left. I've got seconds on the right. That's what I want. Now I pick up my calculator and do the math. And what do we get when we do the math?
600
Is that right? All right. Now put it in scientific notation. And what is that?
6.048 times 10 to the 5.
And any one, it doesn't matter. That is the correct answer. But I'll tell you what isn't the correct answer. That isn't. That's a number. It's lacking units. All right? That's only partial credit. If we had a 5-point problem, I'd probably take a point off because there's no unit. 1 or 2 points off. Because there's no unit on the number. So when you report a number, make sure you report its appropriate unit with it as well. Okay, so that's dimensional analysis. So if you want to pick up your periodic tables, you've got tons of conversion factors in here. So let's do a couple problems. Let's convert 743 centimeters into inches. This is given. This is desired. So this is the way it looks right at the beginning. You know that whatever it is you're looking at here is 743 centimeters long, but you'd like to know what it is in inches. And what is the appropriate conversion factor? 2.54 centimeters equals 1 inch. Yeah, that 1 inch isn't just one significant figure. It would have many significant figures. So it's not going to limit the significant figures in the answer. Let me just, 2.54 centimeters equals 1 inch. So 2.54 centimeters divided by 1 inch is the number 1. And 1 inch divided by 2.54 centimeters equals the number 1. Why is that? This is exactly the same length as that. They are equal. We're expressing it in different units, but if I had, well, let's do it right here. Right? This line right here, that is 1 inch long. It's 1 inch long. It's 2.54 centimeters long. All right? So anything divided by itself is 1. This is equivalent to that. I mean, since it is, I could say since 1 inch equals 2.54 centimeters, I could substitute 2.54 centimeters right here for this. And 2.54 centimeters divided by 2.54 centimeters is 1. This is why dimensional analysis is also referred to as unit analysis. And all I'm doing there is I'm saying you can use this conversion factor in any order you want to. You could put the centimeters in the numerator and the inches in the denominator. You could put the inches in the numerator, the centimeters in the denominator. It does not change the value of those numbers. So which way do we want to put it here? What do we want down in the denominator? Centimeters. Why? Because we want to get rid of that unit. And we want to convert it into inches. So the dimensional analysis tells me, here's what happens to lots of people. They get to a problem like this, and they go, you either multiply or divide. I know it. I know what you do here. You either multiply or divide. And they think they're pretty smart. But they get the answer right 50% of the time. Because they guess, I'm going to divide. No, I'm going to multiply. I'm going to divide. I'm going to multiply. And half the time they get the right answer, half the time they don't get the right answer. Half the time they get the right answer, it spurs them on to guess the next time. Okay? I wanted you to take the guesswork out of your problem solving. If you're on the 4th floor of a hospital in 5 years as a nurse, and you're trying to figure out what medication someone needs to get, do you want to guess? You don't want to guess. Do you know at UT Health Science Center, day one, nursing program, they spend all day on dimensional analysis. That's what they do. They get their students together and go, okay, we're going to show you how to do drug conversions. And we're going to use, I don't know if they will call it dimensional analysis, but that's what it is. It's dimensional analysis. Had one of my students about 5-6 years ago go to UT Health Science Center, and he wrote me an email back. As a matter of fact, I think I got it posted up in Canvas. I think I keep it up there. And he said if there was one thing, or a couple of things I would emphasize, but one of them would be put more emphasis on dimensional analysis because we use it so much in nursing. You can't guess. You have to kind of know. And this lets us know that we divide to get the right answer. What we've got here is we've got our given unit, and what we've done here is we've taken our desired unit divided by our given unit to get the desired unit. That's what we've done. Given unit has gone away. We get our desired unit. So 743 divided by 2.54 equals, now I'm getting 292.519685 inches. But I have, my given unit is to 3 significant figures. So 292.5 is going to become 293. inches. 293 inches. Okay? So I take what my calculator is giving me, now I round it to 3 significant figures because my number given was 3 significant figures. All right. So yeah, you will see me using dimensional analysis over and over and over again. Well, let me get back to my slides and see where we are. All right. Just be aware there are some slides in here explaining what we went over with addition and multiplication, explaining what you do there. Here's some conversion factors. Notice that there are 3, well, there's more than 3, but the 3 main places, 3 different categories of measurements: length, weight or mass, and volume. Those are 3 different parameters that we measure. And you can see the English unit for length, we've got inches, miles, the metric unit, centimeters, kilometers. The fundamental unit in the metric system we'll see in a moment is the meter. For weight, we have grams in the metric system, pounds in the English system, kilograms, grams and kilograms in the metric. Volume, gallons, quarts, ounces in the English system. The liter is the fundamental unit in the metric system. So here are your fundamental metric units. Mass is grams, length, meter, which is right here. This is not a yardstick. This is a meter stick. All right? A yard is right here, 36 inches. So this is bigger, longer than a yard. It's 100 centimeters, or a meter. A meter has 100 centimeters. So a centimeter is 1/100th of a meter. That's length. So the fundamental unit in the metric system is the meter for length. Volume is liter. And then the beauty of the metric system, the English system is random. You know, there's 12 inches in a foot. There's 5,280 feet in a mile. They're just, I mean, if you wanted to write a book on the history of where those numbers are coming from, go ahead. They're just someone came up with them. 4 quarts in a gallon, 16 ounces in a pound, all different kinds of numbers. But the metric system, the beauty of it is it's a base 10 system. All right, so you can keep these in mind: gram, meter, liter. And now you have these prefixes that are going to mean the same thing no matter what you put them in front of. A kilo is 1,000. So you have a kilometer. You write a K. You have a kilometer. You have a kiloliter. You have a kilogram. So kilo always means 1,000. 1,000 meters, 1,000 liters, 1,000 grams. Milli is 1/1,000th. So milli is small. Kilo is big. Milli is small. So a millimeter is 1/1,000th of a meter. What is 1/1,000th of a meter? I just told you centimeter there's 100 of them. 100 centimeters. 60, 70, 80, 90, 100 centimeters. So then what, we got 10 lines from 1 centimeter to the next centimeter. There are 10 lines, so 10 times 100 is 1,000. So every line on this meter stick is a millimeter. From one line to the next is a millimeter. So maybe 20 pages. The thickness of 20 pages. I've never figured it out, but 20, 30 pages is about the height of a millimeter. It's 1/1000th of a meter. You're going to see us use this a lot. Milliliter. Milligram. Where do you come across that unit? In what? Medications, supplements. You take a vitamin C tablet, it's 500 milligrams of vitamin C, or 100 milligrams, or 50 milligrams. So you come into contact with these units, but that's what it is. A lot of times, it's in milligrams. If you see this unit, don't get MC, that's micrograms. That is this 1/1,000,000th of a gram. So don't get that mixed up. If they say selenium should be 10 micrograms in your diet daily, don't take 10 milligrams. You're taking 1,000 times more of it than you should. So those are important units. Nanotechnology is dealing with small units, okay? Well, start kind of getting familiar with these units, these prefixes, and what we are looking at here. Here's your fundamental unit. Here's your prefix. Milliliter, millimeter, milligram, grams. 1 kilogram is 1,000 grams. All right, we started talking about dimensional analysis. Mass, the quantity of matter in an object. Weight, mass times the acceleration due to gravity. We will use mass and weight pretty interchangeably. I mean, if we were to transport you or something from here to the moon, your mass wouldn't change, but your weight would change. You would appear much lighter on the moon, even though nothing's happened to the amount of matter making you up because of the moon's lower gravitational force on an object. So weight has to do with the force of gravity. Mass is really how much material is there. But at sea level, mass and weight are about equivalent. Length, the distance between 2 points. So those are your length, mass, and then volume. How much space does that occupy? Here's volume in the metric system. The definition of a liter. What is a liter? A liter is a volume of space of 10 centimeters by 10 centimeters by 10 centimeters. That's the definition of a liter. So if you take 10 centimeters times 10 centimeters times 10 centimeters, you get 10 times 10 times 10 is 1,000. Centimeter times centimeter times centimeter is cubic centimeters. It's 1,000 cubic centimeters. So 1 liter equals 1,000 cubic centimeters. So 1 cubic centimeter down here, 1 cubic centimeter equals 1/1000th of a liter. It equals 1 milliliter. Milli, 1/1000th. So you end up with this equivalence here, that 1 cubic centimeter equals 1 milliliter. They are equivalent to each other by definition, because a liter is defined as that space, and in that space there are 1,000 of these little cubes, which is 1 centimeter by 1 centimeter by 1 centimeter is 1 cubic centimeter. Okay. On Tuesday we will do density and temperature, finish off chapter 2 and chapter 1, probably start chapter 2. So be ready there, and I'll try to get all the reading assignments open and quiz number 1 open. If anyone came in late, let me know that before you leave.